electrons are successively added to the penultimate shell, that is the second to the last shell. This is unlike the S and P block elements. Let's go again. See you later. The zirconium has verified nothing to convict me. Why? Many talk recklessly, forgetting respect over committing rebellion in national policies. Please call and advise zinc concerning humility. Isn't that amazing? The first D to D what? Transition. Whereby D in the lower level goes to what? Higher level. Remember that, as you can see there on the screen, this is the configuration showing you the S block, the P block, and the D block. 3D9. This is incorrect. So the correct thing should be what? 1s2, 2s2, 2p6, 3s2. So, under this magnetism, there are different forms of magnetism that transition metals can exhibit. They can exhibit dimagnetism, paramagnetism, ferromagnetism, ferrimagnetism, possibly antiferromagnetism, depending on some factors, environmental factors, including temperature. The color you see from any substance is the color reflected by that substance. Those ones you don't see are the color absorbed. We have 7 colors of the white light. Welcome to Sa Majesty Easy World. In this video, I will be demystifying the fascinating topic, transition metals. Here are what I'll be discussing. Number 1, the origin and the meaning behind the term transition metals. Number 2, a comprehensive definition of transition metals. Number 3, easy mnemonics to help you master the 3 transition series. Number 4, insights into the unusual nature and electronic configuration of the transition metals. Number 5, intriguing facts about the transition metals. Number 6, identification of the non-transition members with the D block, that's within the D block, and why they are exceptions. Number 7, general characteristics of transition metals, including catalytic activities, variable oxidation state, formation of complex ion, paramagnetism, and more. Enjoy watching and feel free to drop your question in the comments section below. If you find this video helpful, don't forget to like, share, and subscribe for more engaging content like this. Much love from me to you. Let's take an exciting journey through the chemistry of transition metals together. I promise you, you will love it. Let's go. Transition metals. Why the term transition metals? Literally, transition means changing or passing from one phase to another, or from one place to another, or going across from one end to another. In fact, the word transition comes from the Latin words transire or transitio, which means to go across or a going across. The term transition can be applied when there is a noticeable change in existing scenario. Over here in Nigeria and some other parts of Africa, you often see people replace the word obituary with transition to glory while announcing person's death. This is mainly due to the belief that death is not the end, but a passageway to change from life to afterlife or spiritual realm. Charles Rugliberry, an English chemist, was the first to use the term transition metals in 1921 to describe the series of elements on the periodic table that were changing between stable electronic configuration in their inner shells, mainly those that occur from the 4th row, period 4, that's period 4, that's transition from stable group of 8 to a stable group of 18 electrons in their penultimate shell. That is N equals 3, that is M. That's M share for period 4. In this case, extra 10 electrons are added gradually and successively to the N-1 share to increase the number from 8 to 18 for elements in the D block. Electrons are successively added to the penultimate share, that is the second to the last share. This is unlike the S and P block elements, where electrons are successively added to the last share as you move across the period. This transition also occurs from 18 to 32, where extra 14 electrons are added gradually successively across the period in N-1 share for the elements in the F block. N here is the principal quantum number of the last share. Hold on. This whole thing about gradual transitions from 18, that's from 8 to 18 and 18 to 32 stable oxidation state or stable configuration, sorry, of the inner shells will be clearly explained shortly after now. Now, how many blocks do we have in the periodic table? To explain further why the term transition metals is applied, we have to recheck the position of the blocks of the periodic table quickly. Looking at this majestic periodic table you can see behind me, we will see that there are 4 blocks in the periodic table according to the 4 subshells S, P, D, and F, out of which 3 blocks S, P, and D blocks are distinct and aligned horizontally next to each other, starting from S to P block. The S and the P blocks forms the margins, that's the ends of the periodic table, with the D block in between them. That is, D block is in the middle of S and P blocks. The S block metals, that's the group 1 alkali metals, example lithium, sodium, potassium, rubidium, cesium group. Then the alkali earth metals such as beryllium, magnesium, calcium are far more reactive than the P block metals such as aluminum, lead, tin, bismuth, etc. To move from S to P, that is transition from the very reactive S block metal to the less reactive P block metals like aluminium, you have to pass through certain groups of metal with unique and intermediate properties between that of S and P block metals. These metals are literally called transition metals because they are elements that transition between S block and P block. Both their position and their properties are intermediate between S and P block metals, and hence the name transition elements. So these elements are the D block elements, and that's our topic today. And their inner members from the 4th block called the F block, inner transition elements. Now, all the elements in this D block are metals, including the inner series. This implies that they share the general properties of metals, such as ionization by loss of what? Electron or electrons, malleability, ductility, lustrous nature, good electrical conductivity, and heat conductivity, etc. But they also share some unique characteristics which distinguishes them from the S and P block metals. So to facilitate your understanding of this topic, transition metals, you are advised to watch my introductory video on metals. Revisiting electronic configuration and the periodic table will catalyze your comprehension of this topic too. Now, what are transition metals? What are transition metals? These are elements in the D block of the periodic table whose atoms have partially filled D orbitals. Repeat, partially filled D what? Orbital. The major thing there is partially filled D orbital, or which can give rise to what? Cations with incomplete D subshell. This definition is gotten from the old edition of the IUPAC Gold Book, defined like this in exams, but under IUPAC recommendations, where the groups are numbered from 1 to 18, unlike the common 8 main groups you are used to, that is, the 2011 IUPAC principle of chemistry of chemical nomenclature described a transition metal as any element in groups 3 to 12 on the periodic table. This implies that there are 10 transition groups, which starts from period 4 down to period 7. I repeat, there are 10 transition groups between main group 2A and main group 3B under European recommendation. Under IUPAC recommendation, the transition metal is in between groups 3 and group 12, which starts from period 4 to period 7. So theoretically, there should be a total of 40 transition elements, but because of the fact that lanthanum and actinium, of course, form parts of the inner transition metals, that's the F block. So there are 38 transition metals excluding the inner transition series, that's the actinides and the lanthanides of the F block elements. In situations where the F block elements are included, there are about 68 of them that are considered transition elements, 38 from the D block and 30 from the F block. Now, the explanation of the definition of transition metal. To lay more emphasis, the d subshell contains 5 degenerate orbitals, and each degenerate orbital can hold a maximum of 2 electrons. Now, an orbital means a region in an atom that can hold up to what? 2 electrons. This implies that the maximum electron d subshell can hold is a total of 10. That is 2 times 5. So any d orbital that contains 10 electrons is said to be what? Completely filled. But any d subshell that contains from 1 to 9 electrons is said to be partially filled or incompletely filled. So transition metals are not just any element that have the d subshell, but elements that have the d subshell that don't contain up to 10 electrons in the d subshell. So transition metals typically have ND1 to what? ND9 configuration, either in their neutral atoms or in cation in any of their stable oxidation states. N is the principal quantum number. It is these partially filled d orbitals that is mainly responsible for the unique chemical properties of the transition metals that will be discussed in this topic. With this explanation, it shows that it is possible to have an atom or ions in the D block, that's group 3 to 12 of the periodic table, that is non-transitional in terms of properties, but only transitional in terms of position. This is only obtainable if the element in the D block is in the D block but lacks partially filled D orbital, either by having 0 or 10 electrons in the D orbitals. Remember, to be partially filled doesn't mean not to have the d orbital not filled at all. So let us take a look at the transition series and transition groups and their unusual or unique electronic configuration patterns. There are 3 transition series, namely the first, second, third, and fourth transition series. The first series, also called the 3D series, are in period 4, starting from scandium to zinc. Second series, also known as the 4D series, are in period 5, starting from yttrium to cadmium. Third series, known as 5D series, starts with the lanthanum and ends with mercury. The fourth series, 6D series, contains actinium and other elements, mainly artificial elements, discussed along with the F block elements. Here, I will focus on the first 3 transition series and the electrons present in the D subshell of their neutral atoms. I will give you the mnemonics to master all the elements in the first, second, and third transition series alongside the D subshell electrons. The first series contains in detail the scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Then the second series, that's the 4D series, contains the yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rubidium, palladium, silver, cadmium. Then the third series includes the lanthanum, hafnium, the titanium, the tungsten, rhenium, osmium, iridium, platinum, gold, and mercury. Then the mnemonics for the first to third series. See you later till zirconium has verified nothing to convict me. Why? Many talk recklessly, forgetting respect over committing rebellion in national policies. Please call and advise zinc concerning humility. Isn't that amazing? Group these words into that is, group the words in this statement into 3 to match the 3 elements in each of the 10 transition groups, starting from scandium group to zinc group. The fourth series is excluded from these mnemonics. The statement below contains 30, the statement above, sorry, contains 30 words, which actually represents the chemical symbol of the elements involved, not necessarily their names. Not necessarily the names of the elements. Example, forgetting stands for iron, symbol for iron is Fe, and Y stands for W, symbol for tungsten is W. Now, let's go again. See you later. The zirconium has verified nothing to convict me. Why? Many talk recklessly, forgetting respect over committing rebellion in national policies. Please call and advise zinc concerning humility. Isn't that amazing? The first series is very important also. we can also master it well. See the mnemonics for the first transition series only. Serious tetanius virus causes malaria in cold night condition zone. I take it again. Serious tetanus virus causes malaria in cold night condition zone. So let me show you the configurations over here. As you can see on the screen right away, okay, on the table, as you can see there, what we are going to do now is I will be giving you the number of d electrons. Over here, we will do our counting, of course. So we are going to be considering the distribution of electron, that's the electronic configuration in terms of 1s2, 2s2, how many electrons will be there. See how I'm going to do it. I'm going to count, which is there on the screen already, but I will just repeat it again. I'll be counting in terms of maybe I'll be giving you 1, 2, 3. Now, if you want to count, remember the transition group starts from, according to IUPAC recommendation, starts from group 3 to group 12 over here. But remember that when we say group 3, without the transition metals, we refer to the aluminum group, which is actually, according to European, is the main group, 3B. Okay, but conventionally, IUPAC says we should number them serially. Now, look up here. We will be counting alongside, starting from scandium group. Scandium group means scandium, yttrium, lanthanum, and down to zinc group, which includes zinc, cadmium, mercury, and the other artificial elements I might not know. So remember that this is their d electrons. Over here shows their d electrons, meaning how the d electrons are filled. So while writing the configuration of scandium, it will end in ND1. That is this one here. So let's take a count. Assuming you are partying, you use the term, we are going to use one acronym, which will say no night, no fall. If you party around where you love what is happening in the party, you can confidently say no night, no fall, meaning no daybreak, no day party on, you know. So, but here, if you check from 1 to 10, which of the number rhymes like no nine, 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 no nights, no nights, which is 9, no fall, no fall, which is 4. So if you are counting for neutral atoms, we won't be considering 9, neither are we going to be considering 4. So there won't be anything like neutral atoms will not have ND9, neither will they have ND4 for neutral atom. N here is the shell, why D is subshell, that's the N is the principal quantum number, just like KLM, you know what I mean? So let us move on to clear you. The counting is already there, as you can see. So I'm going to count now. That's why I wrote that number, so that I don't get it twisted. 1, we move by having, counting is 1, 2, 3, 5, 5, 6, 7, 8, 10, 10. Instead of having, so I jumped 4. So no neutral atom is expected to have the 3D4 and then 3D9. These are exceptions that we will now consider when we write the configuration, which makes group 11 have some unusual configuration. In addition, with this group 6, according to IUPAC recommendation, that's transition group 6, chromium molybdenum have unusual configuration. Instead of ending in D4, they end in D5. So you should pay rapt attention very well in that of chromium, which is number 24. Chromium should be normally 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d4 because it's number 24. Remember that scandium is 21, titanium is 22, 24, the vanadium is 23, and this is 24. So if you share electron, calcium is already 20. Looking at this, you're supposed to end in 3d4, but this is incorrect. From what I'm telling you now, we don't have 4, we don't have 5. Therefore, the correct configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, and 4s1. So this is the correct configuration of chromium. The same thing is applicable when you come to copper. Be careful. Copper, in the correct configuration, Remember, what applies for chromium also applies for molybdenum, but not for tungsten. That's why I painted it pink. I will discuss that later. So, but when we come to copper, copper has 20 what? 29. That's copper should be number 29 and zinc should be 30, of course. You are not expected to write one normal thing that one should expect while writing copper is copper 29 should be 1s2. I don't want to use the noble gases to make it easier. I don't want to use the noble gases making it easier. So we have 2s2. I want to go in details. 2p6, 3s2, 3p6, 3, and then 4s2, 3d9. This is incorrect. So the correct thing should be what? 1s2, 2s2, 2p6, 3s2, 3p6. The d is filled before the 3d is filled before the 4s, which is unusual, 3d10 and 4s1. So this is our interest. This is where our interest lies. You see, this is 3d10 and 4s what 1 is a deviation. The same thing is applicable when you handle any other members of the copper group. That's copper, silver, and gold. But the other artificial element there, which is a rotangent, is exception. That's why I highlighted it on green. So this is unusual configuration of the period, the so-called D block what elements. Okay, one good thing about this configuration you're seeing here is that having given you these numbers, I've cleaned everything. Now, you remember that when I said scandium, all these ones, all their configuration will end in D1. All these ones will end in D2. That's what it implies. Then the members of these ones will all end in D5. And these ones also, the coinage metals, the one we use for making coins, will end in D10 also, and the same thing with 12. So that's the significant. Now, the advantage is that the first series is called 3D series, and second is 4D, the third is called 5D, then the fourth series is called 6D. So let's assume I want to write the electronic configuration of molybdenum over here. This molybdenum, how will I know what will happen? Under here, how many electrons does it supposed to have? It's supposed to have 5 and is under 4d. So molybdenum will have 4d5. Now let's take vanadium, for instance. Look at vanadium is here. It will end, the last d subshell will be what? Is under 3d series. So I will write 3d. But how many electrons will it have? It has 3. 3d3. So that's the need for these numbers I gave you, which will help out, like the number for D shells and the names. They are 4D and 3D. Now, can you guess what will end that of a cadmium? Cadmium will end in what? You look at the position of cadmium. Look at it here. This is cadmium. So cadmium is expected to end in, from what I taught you, is under what series? Is under 4D series, and it has 10 at the end. So configuration of cadmium will end in what? 4D10. For this artificial element, look at mercury also. Mercury will end in what? Is under 5D series. It will end in 5D10. So the same thing, if you look at nickel, which is the only one that obeys it well. Other ones I highlighted in different colors disobeys this thing I'm teaching. So if you look at nickel, nickel is in 3D series and the 3D electron is 8. Hafnium hafnium is in 5D series and the d electrons is 2. So it's supposed to end in 5D2. So that's the need of this table. So you have to relate these numbers to write the configuration of what is inside. Now, let us see the distribution of the electrons in the shell. Why we say that they transitioned from 8 to 18. Why do we even call them transition? Their electronic configuration gave them that name, but this is not the type that will give it. Remember, apart from these ones I mentioned here, every other one follows, which means iron here will end in 8. Ruthenium will also end in 8. Osmium will end in will end in 6, please. This is the d electron. The d electron will be 6. We are talking about the last d electron. But if there are, like, if an atom have 3d, before 4D, we are considering only that 4D. The 3D will be completely filled though, but their last D subshell will be partially filled. That is it, what we call transition elements. Okay, so let us see the distribution of the electrons in the shells. That is, in the case of K, L, M, and N, O, P, Q, we have 7 shells. Let's see why they transition, why they misbehave, why they have a total unique behavior from S block and P block. Okay. Distribution of electrons in the shells of transition metals, that is transition metals, that's transition in their inner shells. As earlier mentioned, that the pattern of filling of the shells by electron changed when the D subshell becomes filled. As you move across the periods from right to left. For S and P, electrons are added to the last stroke outermost shell, thereby leading to increase in the number of valence electrons in the D block. A new order is obtained as you move across the period of the D block electrons. Electrons are added to the penultimate shell, that is n minus 1, instead of that of the last shell. The valence electrons remains constant while the penultimate shell expands from 8 to 18 electrons. Now, let's see the electron distribution within the shells of all the elements in period 4. So this period contains S block element, D block element, and P block what? Elements. Now, to illustrate this right away, all right, as you can see there on the screen, this is the configuration showing you the S block, the P block, and the D block. So to make this easier, I will have to put this in writing, of course. So when we look at what we have here, obviously is like this. This is the S block metals, the S block, please. That is for the period 4, of course, while these ones are highlighted on red are the D block. And then this one is the P block. Remember, this also proves why a transition. So when you look at the period 4, it starts with potassium. And potassium, if you look at the configuration, it is 282881. If you look at calcium, it is 2882. That is for S block. But we now move from the S to D. Scandium is D. From scandium, the D subshell started getting filled. And when the D start getting filled, there is an abnormality. There is a transition. And look up here, in that of scandium, instead of that, normally you will expect that if calcium is 2882, you will expect that scandium will be 2883. But unfortunately, as you can see here, it is not so. Scandium rather is 2892, which means electrons are added now in the penultimate shell, that is the second shell, instead of the last word shell. So what we want to let you know here is that if I draw this potassium, in this case, that is, it is expected to have 3 shells, of course. So let me maybe take something like this. If you have potassium, we have 1, 2, 3, and 4. So in potassium, here is 8, and here is also 8, and here is 2, and here is 1. But extra electrons are added in the valence shell. That's the normal thing you obtain in S and P. But in D, electrons will be added. This is calcium. There is 8 here, so there is now 2. So the extra electron added, we move from 1 to 2, but the extra was adding on the last shell, which remains K, L, M, N. So it was on the N shell. But when we come to scandium, you see there is a change in transition. Scandium will now be the same shells: 1, 2, 3, 4. That's why they are all in period 4. This is now K, L, M, and N. Here is 2, here is 8. Instead of here remaining 8, it now increased to 9, and here remains 2. So you now see that we moved from now, instead of adding to the last shell, we started adding to the second to last shell. So that means from 8 to 9. If you move to titanium, it becomes now 10. So we move from 9 to 10 to 11. Are you seeing it? That is for D block elements. And then we jumped 12 and wrote 13 because there is spatial stability that is connected with the copper and chromium group. As I explained earlier, they also disobey when you write the 1s, 2s, including the subshells. But here for the shell, they also do the same thing. So transition methods becomes unique as the only method that successively adds electron to their inner shell, that's their penultimate shell, n minus 1. Remember, when I say n minus 1, they don't add to their last shell. The n here is the last shell. Like here, n here is, for k shell is 1, for l is 2, for m is 3, for n is 4. Do you get me now? So instead of adding extra electron in that last shell, which is 4, they add to 4 minus 1, which is that 3. That is, they add to the penultimate what? Shell. This is the same thing for both first, second, and third transition series, but here I consider that of the first series. So from 14 to 15, 16, there is also another jumping with copper, because I told you there is a unique stability with copper and chromium. So instead of 17, we have 18. We have also 18. We have transitioned gradually. When you move from S to D, you transition gradually from 8 to what? 18, which means you need to add extra 10 electron, but on a gradual process. So if you look at the majestic periodic table, you will also understand. But when we move across to P, let us transition again. We are done with D. Those ones highlighted on yellow now is that of P block, starting from this gallium to germanium to arsenic. They are in P block. You now see that the inner shell, the penultimate shell, remains non-constant. All of them is 18. So the normal thing is that electron should be added on the last shell. So the last shell now is N. It moved from 3, 4, 5, 6, 7. So this has gone back to obey that of S. So S and P, electrons are added successively on their last what? Shell. But for D, electrons are added successively in their inner shell, that's their n minus 1 shell. So the second to the last shell, the penultimate shell, keep expanding while the last shell remains constant for D. And the movement is gradual. That's why we use the word transition again. So there is change in electronic what? Configuration. So I believe you have really understood what I explained here. Okay, to add again, I have to show that using the periodic table, the majestic periodic table, I have to do the same thing, showing you that. I will zoom it well so that you can see the configuration. Okay, the weather is hot. Okay, let me zoom it in so that you can see. So you see the zooming in, it is very clear. Then I have to edit it so you can understand what I'm saying too. So the majestic periodic table is recommended for you. You can order one. It's available in any form at any size. It's very much available. We can send to you anywhere you are the hard copy. If you have money enough to be a dealer on this majestic periodic table, if you have enough money to be a dealer on this majestic periodic table, you can equally contact me. We can give you the soft copy. It's very clear. So looking at this, look at from potassium, we move to calcium. Potassium is 2881, calcium 2882. In that order, scandium now 289. What I just showed you, you move on. So the same thing applies for other P and S, but D have this abnormality in them. So they show us a kind of unique transition from 8 to what? 18. Then if you move to that of F block, sorry, watch well closely. The F block starts from the lanthanum, the cerium, praseodymium, that's PR, that's from 57, 58, 59. If you carefully watch, see the electronic configuration, it was 1892, it becomes now 1992. So for F block, every other shares remains constant, but the third to last share keep changing. That's for F block. You see that 9 and 2 were constant between lanthanum and the cerium. And then you see that when you move there, it becomes 8 and 18 and 19. So I told you earlier that for D block, electrons are added to the n minus 1, but for F block, electrons are successfully added to n minus 2. So that's why we can equally consider the F block and D block as transition metals, because they also show this transition, but the transition is from 18 to 32, but that of D changes from 8 to 18. So that's the difference. So if we move from lanthanum going to the lutetium, you see that the n minus 2 is now 32. Do you get that now? So that is 8. Deviations in the electronic configuration of some transition groups. It is important we recognize the deviations of some transition elements from the normal Aufbau principle and or the Medlong's rule, the n plus L rule, guiding the filling of the orbitals by electrons. Due to the spatial stability associated with ND5 and ND10, and also due to the closeness of the energies of the ND and N plus 1s, example 3D and 4s, there is an unusual pattern of electronic configuration when it comes to the chromium and copper group. In these groups, 3D is filled before 4s and 4D filled before 5s and so on. According to Aufbau principle and Medlong's rule, 4s should be filled before 3D, 5s before 4D. This is because 4s is slightly of lower energy than 3D, but in chromium and copper groups, the 3D becomes lower than 4s in energy due to the spatial stability associated with ND5 and ND10. In view of this, no neutral atom of a transition element will have neither ND4 nor ND9, like I told you earlier, in its electronic configuration. The electronic configuration of the cations can have ND4 and ND9. That's when they lose electron. The configuration of the neutral atoms of the elements in chromium group ends in ND5 and N plus 1s1, while that of copper group ends in, that's the Coinage metal, ends in ND10 and N plus 1s1, and not ND4 and N plus 1s2 in copper, in chromium, and ND9 and N plus 1s2 as of that of copper. Now, there are exceptions to this Medlong's rule. There are deviations to this Medlong's rule now, as I've shown you. But because we say there is no ND10, I mean, there are no ND9 and there is no ND4, but there are some deviations. For example, niobium is number 41. Niobium supposed to end in 4D3 and then 4s, that's 4D3 and 5s2, but niobium ended in 4D4 and 5s1. That's a deviation. Another deviation is tungsten. Tungsten is number 74. That's the atomic number. The configuration is xenon 6s2 4f14 5d4. So likely these two are the only transition metals that have what? D4 in their neutral what? Atoms. So when we say they can't have 4, these two are the ones that deviate. That's why I highlighted them in the table you can see there. So niobium deviated together with what? Chromium. Not chromium, together with that means niobium have D4. Okay, another deviation is platinum. Platinum is in neutral state, has ND9 in its neutral state. Artificial elements like siabongium, I don't know how to pronounce siabongium, of course, that is number 106, also have this ND9, but that's not, it has also 6D for that siabongium. And even wrong, rotengine 111 also is artificial element. It can also have ND 6D9, but this can vary. Do you understand me? I'm not interested in that of this artificial element. Then palladium also have unusual configuration from other from other transition elements, in the sense that when we say it has unusual configuration in ground state, it has what we call, that is, it is number 46 and it ends in 4D 10 5s0 instead of 4d8 5s2 as expected from alpha in elements in period 4. because the last share is O share. It has 4 shares. That's why it's in period 5. Sorry, that's why it's in period 5. So the distribution of electron of palladium is, that's distribution of electrons in the shells of palladium, that is in the shell of K, L, M, and N, is 2, 8, 18, 18, 0. Imagine that. So it's the only element that has 0 electron in its last share in neutral state without losing or gaining what? Electron. So palladium is unique, and that what makes palladium unique. Then the electronic configuration of the first transition series. I've told you that we have shown you those ones. I'm taking a look at from scandium to zinc. Everything falls in order except you watch that copper and chromium group. Be careful for exam. And remember, understanding these configurations will automatically help you to understand the chemistry of these the unusual properties of these transition what elements. You understand that? So don't joke with this. Now, the significance of understanding clearly, I repeat, the electronic configuration of the D block elements is that it will lay the foundation for you to understand and predict the characteristics of each of the transition elements, and also help you to explain the unusual behaviors of some D block elements and their cations. Now, let us look at non-transitional members of the D block elements. Having understood the definition of transition elements and the deviations of some transition groups from normal rules governing electronic configuration, it is evident that the copper group, that is group 1b or group 11, and the zinc group, that is group 2b or group 12 elements, have completely filled d orbital instead of partially filled d orbital. The partial filling of the d orbital is the major criteria that qualifies an atom or a cation as transitional. For any atom or cation to exhibit the full characteristics of transition metals, it must have partially filled d orbitals and not either empty d orbital, that's nd0, or fully filled, that is nd10. In view of this, the 2005 Red Book allows for the group 12 elements to be excluded since none of their atoms or their stable cations possesses partially filled d orbitals, rather fully filled d orbitals. But 2011 principles included group 12 since they exhibit few properties of transition metals, such as formation of complexes with ligands. The following atoms and ions are found in the first transition series of the D block but are considered non-transitional. With reason, scandium 3 ion is non-transitional. Why? Because it has 0 electron in the d orbital. Another one is zinc 2 ion. It has completely filled d orbital, that's nd10. Then zinc atom is also non-transitional. Then copper 1 ion is also non-transitional because of completely filled d orbital. And again, copper atom is also non-transitional because it also has nd10, that is completely filled what? D orbitals. Okay? So as we move on, you seeing these configurations will help you get what is happening. The same thing is applicable to other atoms and ions in the same transition groups with the elements listed above in second, third transition series. Example, silver ion and silver metal are non-transitional too, just like copper 1 ion and copper metal. Note, copper 2 ion is transitional because it has partially filled d orbitals. The configuration ends in 3p6 3d9. This is possible for transition cations, but not for the neutral atoms. When I will discuss why transition metals exhibit variable oxidation states just shortly, I will explain the patterns with which the transition metals lose electrons during ionization. So these atoms and ions listed as non-transitional will not exhibit most of the common characteristics of other D block elements because of the reasons mentioned above. Examples: scandium 3 ion, zinc 2 ion, silver ion, and all are all colorless, or as opposed by the normal transition cations, which are all colored. So let us look at general characteristics of transition metals. We look at the general characteristics of transition metals. We earlier mentioned that they share the same physical property. Most of their properties are similar to that of S and P block metals because they are metals. For example, they all ionize by the laws of electron or electrons. That gives the definition for every metal as what I call mile. That is, metals are mile, M-I-L-E. M for metal, I involves L, loss, and then E is the last one. So metals are elements that are ionized by the loss of electrons. So metals are mile. You can use that acronym. But let us use those characteristics that are unique, that distinguishes transition metals from other S block metals and P block metals. Number one, variable oxidation state. What is an oxidation state? Oxidation state is a measure of the number of electrons an atom has gained or lost when it bonds or combines with another atom. It shows the net charge an atom would have when it gains or loses electron or electrons. These charged states are called ions, which are formed by the process called ionization. This involves either the gain or loss of electrons to form positive or negatively charged ion respectively. Transition metals, just like every other metals, ionize by the loss of electrons. S block metals can only lose their last s orbital electron, which is also their only valence electron during ionization, either in all or none manner, meaning that they either lose the whole last share electron or that they don't lose it at all. So this gives the S block metals fixed oxidation states. For example, sodium has one electron in the last share. Sodium will only lose that last share electron to become sodium ion. So we don't say sodium 1 ion because the only possible oxidation state of sodium is +1. Calcium has 2 electrons in the last share. Calcium, and that is in the S, that's 4s2. It's the calcium either loses the whole 2 or don't lose at all. So calcium have only stable oxidation state, which is calcium 2 ion. Now, transition metals in other hand exhibit variable oxidation states because of the availability of the Nd and N+1s electrons for bonding. Their valence electrons are in two different sets of orbitals, the last d and the last s orbital, with a small energy difference between them. The small energy difference allows for successive removal of electrons from both s and d orbitals, allowing transition metals to exhibit multiple oxidation states that are consecutive. Example, ion 2, ion 3. That's +2 and +3.
Manganese has the highest possible oxidation state of +7 for the first transition series. Manganese is number 25, and the configuration ends in 3d5 and 4s2. Both the 3d5 and 4s2 electrons are all available for bonding. In the order, I want to show you now. Okay. In this order, the pattern of ionization, if it is for S and P, that 3D, remember the 3 is in the share before the 4 because the 4 shows N, while 3 is for L. You know, KLMN, I've told you, is in the second share. So from the screen, we have that the scandium ends in 3D5 and 4s2. Remember, this 3 is in the shell. If we write K, L, M, N, principal quantum number here is 1 for K, 2 for L, then 3 for M, and 4 for N. So it means that these 3D electrons, thus these 5 electrons are in the penultimate share, while this 2 electron is the only electron in the last share. Therefore, if you want to write that of scandium, remember that that of manganese, this is the electronic configuration of manganese, which is number 25. What we are saying is that what matters is the end of the configuration, but let's just, for the sake of clarity, 2s2, 2p6, 3s2, 3p, 6, then 3D, 5, 4s, 2. So this is the one in the last shell. Now, what we are saying is that the pattern of ionization is that both these 5 and these 2 are all available for bonding, and that gives it the variable oxidation state. So it can lose one of the, out of these 2 here, it can lose that 2. That's out of these 4s, 4s electron. Manganese, can lose 1 to form what? Manganese 1 ion, which is not other stable. Then it can lose the whole electron in the 4s to form manganese 2 ion. Remember, the transition metals in general they will lose their n plus 1 s electrons before losing their nd electrons. So these are the only this is the only atom, like I said earlier, the only group of element that loses electron both in the last shell, which is n shell here, and also in the second to the last shell, which is m shell. So if it is for the second transition series, they will lose from both the fourth shell and fifth shell. But for S and P, they lose only from the last what? Shell. Okay. So now, if manganese loses 3 electrons, meaning it will lose 2 from this S, it will lose 2 from this S, and also lose this 5 over here. So maybe I use a highlighter. It will lose both these 5. 1 out of these 5 and 2 here. That will give you manganese. You now get plus. You get plus 2 when the whole 2 electron is lost. When 2 electrons from 4s is lost and 1 from D is lost, you get plus 3. When it loses 2 from the 4s and loses another 2 from the 3D, we get what? So let's make it again. 3D and 4s, 2. So if this 4s2 is lost with 2 atoms from 5, it gives us manganese 4. If it loses 3 from this 5, and it must lose the 4s before losing the 3d, all the 4s will go. So it's possible to lose all these 5 plus 2 is 7, to exhibit plus 2 plus 3 plus 4 plus 5 plus 6 and plus 7. So we have manganese 2, we have manganese 7. So the variable oxidation state of what? Transition metals is because they have the ability to lose both their what? Their last share electron and some of the electrons in the D what? Subshare. So this, the explanation I gave you now gives you the reason why some of these things exhibit what? Oxidation what? Some of the transition elements exhibit variable oxidation states. Am I communicating now? So in this case, what I've just explained, that this implies that transition metals don't just lose electrons from their last shell, but also loses electrons from their inner shells. Specifically, they lose electrons from both their last shell and the penultimate shell. In their last shell, they lose electrons in the S subshell, and in their penultimate shell, they lose electron or some of the electrons from the D subshell electrons. This is unlike S block and P block elements that only lose electrons from their last shell. These elements cannot lose their inner shell electrons during ionization. So that is it for variability of the oxidation numbers of transition element. Then the next chemical property is they have catalytic property. They have catalytic what? Property. As we know that catalyst is anything that alters the rate of chemical reaction, either by lowering the activation energy or affecting other things that will make the reaction rate either faster or slower. So let us explain why most of the transition metals and their compounds can act as what? Catalysts. Now, transition metals and their compounds act as catalysts for most chemical processes and industrial processes. This is mainly due to their ability to exhibit variable oxidation states. Transition metals and their compounds can easily lend or absorb electrons from other molecules, which enables them to change their what? Oxidation states. This implies that they can undergo oxidation and reduction by transferring what? Electrons. This ability, when used as a catalyst, facilitates the transfer of electrons between reactants by mediating these electron transfer. Transition methods lower the what activation energy of the reaction and speedens up the reaction rate. Note that after catalysis, transition metals revert to their original oxidation state to remain chemically unchanged. So transition metals can also form complexes and reactive intermediates to alter reaction rate. They can slow or prevent unwanted reactions by forming stable complexes with the reactants involved, stopping their conversion to the desired what? Products. Examples of reactions stroke industrial processes catalyzed by transition metals or their compounds. Number one, Haber process in the industrial production of ammonia. They use finely divided iron as a catalyst. Number two, contact process in the industrial production of sulfuric acid uses vanadium 5 oxide as a catalyst. Then the next number, this is 3, Bosch process for the industrial production of hydrogen gas from water gas uses iron 2 oxide or chromium 3 oxide at 450 degrees. To be precise, this applies in the second stage of the Bosch process, which involves water gas shift reactions to increase the yield of hydrogen gas. The next process is the Osteward process. This process is applied in the industrial production of nitric acid by the oxidation of ammonia. They use platinum or rhodium as catalyst. Then decomposition of hydrogen peroxide, which is common, uses manganese 4 oxide or even KMnO4 as catalyst. Then the production of margarine, that's margarine from vegetable oil through the hydrogenation of alkenes uses nickel or platinum as catalyst. Then Wacker process. Did I hear you say Wacker process? This process is applied in the production of acetaldehyde from the oxidation of ethene. Uses also palladium 2 chloride or copper 2 chloride as catalyst. Then even the thermal decomposition of potassium trioxochloride 5, which we do in the laboratory preparation of oxygen, uses manganese 4 oxide as catalyst. The Fischer-Tropsch process for the production of synthetic liquid hydrocarbons. Synthetic fuels also are produced by this process from mixture of carbon 2 oxide and hydrogen gas. Commonly uses cobalt. You can also use iron and ruthenium as catalyst, but cobalt is often the most active. Then, number 3 chemical property is formation of complexes.
What are complex ions? Complex ions are ions with metal cation with a ligand that is coordinated to it. So the bond holding the ligand and the metal cation, the central metal cation, is coordinate covalent bonding. So one should note this. What is a ligand? A ligand is any species that can donate a lone pair. In other words, Lewis bases are perfect what? Ligands. Now, when transition metals bonds with any species that can donate a pair of electrons, they form ions known as complex what? Ions. Now, how do we know those ones? From your covalent combination, you can now recall that there is what we call lone pair and bond pairs. So those lone pairs are the one that comes from an atom that do not participate in covalent bonding. But shared pairs of electrons are called the what? Are called the covalent, normal covalent bond. So when you look at water molecule, which is H2O, you find that there is 2 lone pairs in the oxygen atom when both two atoms of hydrogen bonds with 1 atom of oxygen. Ammonia also has 1 lone pair. Chloride ion Cl- also can donate a pair of electrons. So these 3 acts as Lewis base and therefore they are perfect ligands. When they come in contact with ions of the transition metals, that is the transition metal cations such as copper 2 ion, zinc 2 ion, they form complex what? Ions. So the question might be coined in this way. Copper 2 ion forms complex ion in the following, with the following, sorry. You now look at any of the options that contains a lone pair. If ammonia is there, you answer it. Or they might twist it and tell you water can form complex ion in the presence of which of the following. You are looking at what now? You are looking at the presence of what? Any transition cation, such as cobalt, such as copper 2 ion, such as zinc. So remember the test for zinc, test for copper 2 ion, all relies on this principle, their ability to form what? Complex ion. Now, the next property of transition metals is paramagnetism. Paramagnetism, or rather what I will call magnetism, sorry, is magnetism. So under this magnetism, there are different forms of magnetism that transition metals can exhibit. They can exhibit dimagnetism, paramagnetism, ferromagnetism, ferrimagnetism, possibly antiferromagnetism, depending on some factors, environmental factors, including temperatures. For you to understand this, you can watch my video here on the channel separately on magnetism, treated in details. So, well, I'll brief it here. Remember, all these properties, all these characteristics of transition metals result from their partially filled d orbital. Now, a transition metal can be paramagnetic only if it has at least an unpaired electron in the d orbitals. So when the d subshell have at least one unpaired electron, such substance is said to be paramagnetic. Then paramagnetism is the tendency of any substance to be attracted to external magnetic field. That is, if you bring them closer to magnet, they will attract, or the magnet will attract them. Such as iron is paramagnetic, but zinc is not attracted to magnets. But you might think that the one used for roofing sheets attracts magnets. Yes, because it's iron coated with zinc, not pure iron. So why is it that zinc is not paramagnetic? When something is not attracted to magnetic field, you call it dimagnetism. So zinc is dimagnetic, while iron is paramagnetic. Why is zinc dimagnetic? Because it has completely filled d orbitals. Remember in the beginning I told you that the partially filled d orbital gives all these properties to transition metals and their cations. Copper 1 ion is also dimagnetic because it also have 3d10. The same thing applies to silver metal. Silver metal, pure silver metal, is dimagnetic, therefore it should not be attracted to magnets. But cobalt, nickel are purely paramagnetic. So you go ahead and study more of this. Remember, the secret is the presence of what? Unpaired electron in the d orbitals. Next property, next characteristics of the transition metals is they form colored ions. The ability to form colored what? Ions. Now, remember that color perception in science is due to absorption and reflection of light, why the different wavelengths of visible light. So when we have the visible region of white light, because of the partially filled d orbital of the transition metals, they can absorb some wavelengths of white light and reflect some. The color you see from any substance is the color reflected by that substance. Those ones you don't see are the color absorbed. We have 7 colors of the white light. Like you are seeing this yellow I'm wearing because of the fact that that particular point that is yellow is doing what? Is reflecting the yellow region of white what? Light. So because of the partially filled d orbital, there is what we call d to d transition. I repeat, d to d transition leads to what? Formation of colored what? Ions. When there are d to d transitions, meaning they will absorb part of the white light and move from, electrons will move from lower d to higher d. To illustrate this, and when electrons absorbs energy, they become excited. So that excitation will enable them to absorb some parts of the white what? Light. And when some parts are absorbed and some are reflected, the part reflected is the one you will see. Like copper 2 ion reflects blue, and that's why they appear what? Blue. So when there is ability of that atom not to reflect any of the white light, it becomes white and colorless. For example, those of them that have completely filled d orbital, they don't have this d to d what? Transition at all. So what brings about formation of colored what? Ions by the transition metals due to d to d what? Is what we call d to d what? Transition, whereby d in the lower level goes to what? Higher level. Remember that d have this. So d orbital has 5 what? Subshells. This subshell has 5 orbitals. 1, 2, 3, 4, and 5. So we have 1, 2, 3, 4, and 5. Okay. So each orbital will have maximum of 2. Let's take a look at the so-called zinc. Zinc is number 30 and the configuration ends in 3d 10 4s what 2. What matters is the D. If you come here, it will have spin up, spin down, follow the rules, then we have down, down, down. So there is no transition. But when we come to manganese or come to nickel or iron, which is number 26, that is iron, Fe, we have that Fe should end in 3d6, of course. The ending is 3d6 4s2. In this case, what do we have? There are 5 of them, 2, 3, 4, and 5. There should be 1, 2, 3, 4, 5. And over here, you see, what is happening is that when this is exposed to white light, there will be transition from this, because this is not completely filled, meaning apart from the first suborbital, these ones are not filled. There is still space. So there is chance that electron will move from here to here. When it absorbs some part of the white light, it transitions, it moves, D to D transition. When it moves, it now reflects some of the energy not absorbed, some of the wavelengths not absorbed, and the color will appear depending on the wavelength of the white light reflected. But when it's completely filled, like here, in that of zinc, there won't be any transition. You can't move here because it's filled up already. You can't say that my room is filled up. You go to your neighbor's room that is also filled up. There is no transition from lower to higher. So this is also why those ones that are called non-transitional, such as scandium, what? Scandium 3. Remember, scandium 3 is colorless because it has 0d electrons. There is no electron in the D block, not to talk of transitioning at all. Why? Because the so-called 3D scandium 3 ion, you know that the electronic configuration ends in 3D1 and 4s2. So scandium 2 is transitional because it will lose only these two. But scandium 3 is non-transitional because it will lose these two and lose this one again, which leaves us with 3D0. There won't be any transition, remember. And this is also why I'm trying to explain why scandium 3 ion and the zinc 2 ion will also remain non-transitional. In zinc 2 ion, what should be lost is this particular 4s, these two electrons, leaving completely filled the orbital. So the same thing is applicable for copper 1 is still 3D, but copper 2 is colored. Why? Copper 2 is now ending in 3D9. Reason is because copper 2 atom, copper 2 please, copper atom originally have 4 S1 and 3D10, the atom in neutral state. Okay, the neutral state it ends in 3D10 and 4s1. So may looking at this, if you check, when we say copper 1, it loses this s, this one electron in s, and it is still 3D, so it is non-transitional. But when we say copper 2 ion, it means it will lose this one and lose another one out of this 10 to remain 9, leaving us with what? 3D9. 3D9 will now have what? At least a lone unpaired electron, 1, 2, 3, 4, 5. That will lead to transition in 1, 2, 3, 4, 6, 8, and 9. So if you expose this to white light, there is tendency that this one will come up here. If it absorbs, this electron will absorb energy. Remember, that's what we call excitation, transition. You must absorb energy before you go to higher energy level. So when this absorbs energy, it climbs up. And then the energy it did not absorb from the white light, the wavelength not absorbed, will be reflected. And probably it reflects what? Blue. And that's why copper 2 ion is blue. But zinc 2 ion is colorless, scandium 3 ion is colorless. What about scandium 3? What about scandium 2? Will it be colored? Yes, because it will have 3D1 and there will be transition from that first bar to the other, so it can give you color. Now, the last but not the least should be the physical property like melting point and boiling point. The melting point and boiling point, the last is the melting point and the boiling point. Just like we have that metals generally have high melting point and the high boiling point, but there are what? Exceptions. All the transition elements are metals and they exhibit relatively high melting point and high boiling point, with the exception of mercury, which is the only liquid metal at room temperature. Then zinc is also too low to be compared as a transition metal. Apart from these few ones, all other ones have high melting point and high boiling point. Reason is because of their smaller atomic size. The smaller the size of an atom, the smaller the atomic radius, which also is attributed to increase in nuclear charge. And this will lead to increase in metallic what? Bonding. So the high metallic bonding automatically gives it higher energy. For you to break the metallic bond, you need to supply a lot of heat, and that gives them high melting point and high boiling point to compare their corresponding S block metals. For instance, if you look at period 4 still, because we start with period 4 because that's the only period that contains the elements from S, P, and D. But period 2 have only element from S and P. So period 4, I mean for period 2, period 3, period 1, all S and P. But period 4 now, that's where the three blocks comes in. Is when you go to about period 5, period 6, that's where the F block comes in. But that's just by the way. What I'm explaining is that if you look at potassium and calcium, their melting point is very low. Potassium is as low as 63. That of calcium I can't recall off head. But when you go to scandium, as you move across the period, the boiling point and melting point increases drastically. What did I say is the reason? Because of corresponding increase in the metallic bond caused by reduced atomic what? Size. Thank you for watching. Please don't forget to subscribe and share this video. You're going nowhere without helping us. Help us and help other people. Spread the light. Love you so much.